Hello class, we are continuing on our journey of the pulmonary system. We've talked about the diffusion barrier, we've talked about volumes and ventilation, and now we want to talk about a specific aspect of ventilation, and that is how ventilation affects partial pressures. Another way to talk about partial pressures is to use the term blood gases, which is what I have right here. So basically we have two learning objectives. Describe the relationship between alveolar ventilation and PCO2. And is this relationship the same for alveolar ventilation and PO2? So remember, if we take our tidal volume times respiratory rate, we get a total ventilation, or a minute ventilation. Remember, we put a little dot on there to show that's a ventilation in mils per minute. But the tidal volume has two parts. It has a dead space volume and an alveolar volume. And if we know our dead space volume and we subtract that from our tidal volume, we get alveolar volume. And if we multiply that difference times the respiratory rate, well, then we get, here, an alveolar ventilation. This is the air that's going into the alveoli and participating in gas exchange. And a typical alveolar ventilation should be about 4 liters per minute. Now, the other thing I want to talk about is that physiologists don't really talk about percentages of oxygen or moles of oxygen. We use something called a partial pressure. So, if you know the total barometric pressure, and you know the percentage of the barometric pressure that's due to CO2, you can multiply those two and get a partial pressure of CO2. Same with oxygen. If the environment has a pressure of 760 millimeters of mercury, and 20% of the environment is O2, then we can take 20% of 760, meaning the ambient partial pressure of O2 is about 160 millimeters of mercury. And about 599 would be the partial pressure of nitrogen, and another 1% is everything else, CO2 and argon and all those other things. All right, so we're using partial pressure like a concentration, and we want to know how ventilation influences that relationship. So here's a person's lungs right here. There's the lungs, we have the dead space, and we have the alveolar volume. And there's the pulmonary blood going in and picking up oxygen and releasing CO2. And now we have oxygenated blood going back to the left heart. All right. So let's say we have somebody breathing in and out of a spirometer. This is a spirometer. You see it's a bell of air. So here's some air in here in a column, and the top to that column floats in some water. This is water right here. And as we breathe in and out, the bell goes up and down. That turns a pulley system, which then writes on a rotating drum. This is an old-fashioned spirometer. Maybe some of you have been in a lab where they still use these old-fashioned spirometers. What we do now is have people breathe into an electronic device, and so it's a digital spirometer. All right. The thing is, there's very little CO2 out here. We just say zero CO2 in the environment. And so any CO2 that's being released from the pulmonary system comes from metabolism. So some of you may have had me in other classes and know I have a little saying, CO2 comes from you. We assume atmospheric CO2 is about zero, and we assume any exhaled CO2 is a reflection of our metabolism. All right. If the part of ventilation that participates in gas exchange is the alveolar ventilation, and I know the percentage of CO2 in the alveoli, then I can get something called a CO2 ventilation or VCO2 production. Then I can rearrange that and I can say my alveolar ventilation is directly proportional to my exhaled CO2. So the more I breathe, the more I'm going to get rid of CO2. I'm going to get rid of that CO2 from my body. That's going to mean the concentration of CO2 in my alveoli is going to go down. So then we have this little equation that we can derive from the equation I showed on the previous slide. So remember, we need little dots. So alveolar ventilation is going to equal VCO2, CO2 production, divided by PCO2 times a constant. And what I've basically done here is taken fractional concentration and turned it into PCO2, because PCO2 is like a concentration. Already? So notice here's alveolar ventilation, here's PCO2. There's an inverse, why do I have indirect here? There's an inverse relationship between alveolar ventilation and PCO2. This would suggest that the more I breathe, the lower my PCO2 is. And the less I breathe, the higher my PCO2 is. Now, the thing is, when we look at alveolar gases, we have to think about how the gas comes into the dead space and gets moistened. So we have to subtract off water vapor. And now we have an equation that's atmospheric pressure minus 47. So PCO2 is related to atmospheric pressure minus 47 times CO2 protection divided by alveolar ventilation. And once again, we need dots to show their ventilation. So we have an inverse relationship. If you breathe more, this number is going to go down. However, if you breathe less, then this number is going to go up. Now, do we have a similar relationship for oxygen? Not quite. Here we have PaO2, alveolar PO2, is equal to, inspired PO2. So here's the difference. We're assuming the atmosphere has no CO2 in it. We know the atmosphere has oxygen. Of course it does, about 20% oxygen. So the partial pressure of what we inspire minus what we're using, because VO2 is oxygen uptake, and again, these are ventilations. So the more we breathe, the more we're going to take in oxygen. We're not necessarily going to use any more of it, which means our PaO2 is going to build up. Now, let's take these graphs, stick in a bunch of numbers and see what the graphs look like. Oh, I love this graph. This is like one of my favorite graphs in the universe. See, our x-axis is alveolar ventilation in liters per minute. A typical alveolar ventilation, 4 liters a minute. If I breathe too much, that's an activity we call hyperventilation. If we breathe more than we need for metabolism, we are hyperventilating. That means our alveolar ventilation is above 4. Look what happens. The more we breathe, the more we expel CO2 because we're blowing it off. So PCO2 goes down. The more we breathe, the more we build up O2 because we're bringing it in faster than we're using it. PO2 goes up. Alrighty. Now, if I don't breathe enough, then I'm hypoventilating. If I'm not breathing enough to match what I need for metabolism, then I'm hypoventilating. If I'm hypoventilating, then I'm not blowing off CO2 and my PCO2 goes up. If I am not ventilating enough, I'm not bringing in enough oxygen to match my metabolism and my PO2 goes down. Notice a normal PCO2 should be around 40. A normal PO2 should be around 100. So we're at our normal values of PO2 and PCO2 when we're breathing appropriately. If we breathe too much, O2 goes up, CO2 goes down. If we don't breathe enough, CO2 goes up, O2 goes down. And the caveat is that the relationship between alveolar ventilation and CO2 is much stronger. If you double your ventilation, your PCO2 is cut in half. How do I know that? Well, this diagram tells me it is. If I were to increase this 2 times, if I were to increase it 2 times, then this would go up 2 times. The problem is this relationship isn't sustained with oxygen because I have to take into account that I'm bringing in oxygen. So I could double this. I could double my ventilation, but I will not double my PO2. I'll increase it, but I won't double it. So this is a very, very strong relationship. The other beautiful thing we learned from this graph is that there are 2 reasons why we need to control ventilation. Whether we're doing it physiologically on our own ability, or whether a healthcare professional is ventilating for us, either with one of those squeeze ambu bags or with a mechanical ventilator. The reason why you need to breathe enough has both to do with O2 and CO2. Let's get even fancier here. All right? If you're hypoventilating, you're not bringing in oxygen. You need that for your metabolism. But the other problem is you're not getting rid of CO2. And CO2 is a waste product. If you have too much CO2 in your body, what happens? It causes acidosis. So when you have a patient that comes into the emergency room, they're fixing their roof, they fell off the roof, they hit their head, and they damage their respiratory centers, and now they can't breathe enough. Yes, you have to put that person on a ventilator so that they'll get oxygen, but it is as important that you put that person on a ventilator so that they can get rid of their CO2. Likewise, you have a person, maybe they have liver failure, and the waste products from liver failure is just stimulating the living daylights out of the respiratory centers, and they're hyperventilating. The reason why you need to intervene is not just that they're breathing too much and they're getting too much oxygen, though in this case that's really not the issue. What's the issue? The issue is that they're blowing off too much CO2, and that's making them alkalotic. That's removing too much hydrogen ion from the system. So I wanted to do a standalone presentation just on this to realize how important this graph is and how important alveolar ventilation is to both PO2 and PCO2. I'm going to end it here, and I'll see you next time.